Thank you. Welcome to the Building the New Search Engine talk. In purple, that's a feature. You have to trust me on that. So briefly about Bloomberg and a bit about me. It almost looks like artsy now with the purple on. I didn't quite intend that effect. Bloomberg is a technology company. Our focus and strength is data. You probably know Bloomberg through the channel you see on TV, but the biggest product we do have is what is called the terminal, which is a one-stop shop for people in the financial industry, as well as governments and economists and other people in other professional disciplines to get data, visualize data, do calculations on data, and pretty much carry out their workflow based on the screens that the terminal provides. We also offer other vertical portals on the web for various different disciplines, like if you're interested in the government, or if you're a lawyer interested in litigation, and those form our customer base. A bit about me. I started Bloomberg 9 years back. I'm now the team lead for the news search team, which is responsible for the search, alerting, and ingest infrastructure for news. There are other teams within Bloomberg which work on search as well. We even have a generic platform which allows people to build applications based on search. Steve, my colleague, is responsible for that. But this talk will mostly focus on the news side and how we went about building the new search platform. I started with Solr Lucene, pretty much sort of like with Hello World 3 years back. We found during the course of our project that we needed to deal with Solr and Lucene and its internals a lot. We kept coding, making changes. I'm now a committer with the project with Apache Solr Lucene. We actually have 2 more committers in the company now after me. This talk is going to be a lot about the changes we have done to Solr as well, and about what kind of challenges we faced and so on. So even before I go into what we did, this is pretty much a typical search ecosystem, if I would call that. What happens when you search? You go to any search engine, you start typing, the system starts suggesting queries as soon as the user is typing. You end up typing some query either based on a suggestion or you type it out yourself. Then the system tries to understand the query and tries to figure out what you exactly meant using NLP, entity recognition, disambiguation, spell checking, etc. At the end of it, you get a more structured query which looks for keywords and metadata of documents. You search for that. You get results. Often you get results which are in millions. Then your biggest problem then is to sort the results as the usage dictates. Sometimes the search could be, sort order could be something very simple, like show me in reverse chronological order. But the most common one tends to be by search relevance, as in how relevant is this document to the user. You also have some cases where you need more diversification, or you want sort of like some results promoted of others. In essence, you get an ordering of the results based on the results you have retrieved. In many cases, including ours, and this forms a more exciting part of what we do, there is a real-time element to it where you need to just, but you also need to display alerts as soon as a new search result comes up. And then on top of that, you need to expose facets and be able to tell people what else to search on. And finally, you end up sometimes recommending searches and recommending stories as well for people to do this. In this talk in particular, I'm going to focus on just 2 lines of it. As many of you probably already know, each one of this stands a talk by itself. You can talk for an hour almost on how such an infrastructure is built, what the entire sort of stack behind it, and so on. There's a lot to be talked. But in the interest of time, I'll be focusing mostly on the searching and sorting, more to do with what Solr Lucene does. As with everything, the challenge always is not just in implementation, but also the scale of it. And Bloomberg has its own share of challenges. We have around 27,000 customers. Almost all of them use news. We get around 10 million searches a day. Not the greatest amount that you've ever seen quoted, but the main challenge there is that the search needs to be real-time as well as need to respond fast. So our average response time is around 180 milliseconds. The mean is actually less than 100, which is a different, entirely interesting story as well, which I'll skip at this point. We get over 500 stories a second, sometimes at peak rate. It tends to be very spiky traffic, as news often is. And the real challenge here is that these results need to be available for search in around 100 milliseconds. If you're familiar with search, this is often a big dilemma you face with how fast can your search results be retrieved and how real-time is your search, really. Overall, we have an index of around 500 million stories. Obviously, with news, like the older the story goes, sometimes it's not just important, and we sometimes discard stories. And also, as I mentioned, this is a real-time system, so whatever we do to get initial set of results, we also need to alert on top of that. Especially, we have a very strong case for chronological search results. We do relevant sorted results as well. Both are equally important use cases. But especially for the chronological search results, day traders, for example, in the financial industry, expect results to show up on their screen as soon as it arrives. And this holds good for any search that they come up with. It could be arbitrarily complex. We have around 1.5 million of those safe searches. And we endeavor to provide alerts within 100 milliseconds of the story coming in, either in front of their screens or there are other mechanisms available as well. In particular, what's kind of kept us busy in the last few years and is still ongoing is we used to have an existing system which was based on a proprietary system. It was past its end of life. It was inflexible. It had no scalable relevant sorting. It had a lot of other limitations like you typically would associate with a third-party software. So around a few years back, around 3 years back, we started looking at other solutions, especially open source solutions. And we did a bit of a survey, and we finally ended up with Solr Lucene. For a few reasons, many of you probably know this. It's rich in features, extensible, it's actively maintained. It's free software, which means that we can contribute back to it. We can modify the source to our requirements. And as a part of this, one of the challenges was that we had to build an from-scratch alerting backend, which we did based on Lucene and Luwak. I probably won't have too much of a chance to cover the alerting backend, which, as I said in the beginning, deserves a talk of its own. But it's just as exciting as this one. The entire exercise was not just something we did to change the backend, but it was an architectural revamp. One of the driving goals of this change was to make the entire system scalable. And this is especially important in the kind of search that we do. News tends to be spiky. Our requirements change quite dramatically in quick succession. And often you're left with a place where you need to scale quite heavily, right? I need to be prepared for a case where tomorrow I might be getting 10 times the amount of load or 10 times the number of news stories. And I should start thinking ahead in terms of what I should be doing then. So this architectural revamp also tries to make this entire system scalable and also maintainable as well, so that it's very easy to add metadata, reindex all the data, and so on. So here's where I did it in 4 easy steps. Easy being subjective. Make it work. Make it fast. It's surprising how many people sort of like don't think it's important. The first, we spent around a year on the first and more than a year, 1.5 years on the second. Make it stable. That's important. And then make it better. Thank you very much. Have a nice day. OK, let's go deeper. So before I go any further, let's try to understand what actually goes into the system. This is what tends to be typical of a search engine. You have a document and you have a query. In our case in particular, we have news stories, research documents, tweets, anything which kind of falls into news. Sometimes doesn't fall so much into news, things you're interested in. Public stories mostly, but it doesn't have to be. I'll talk about that in a bit. For every news story, there's a story body, obviously. There's a headline, there's a time of arrival, there is source. There are tags associated with the story. Throughout this talk, I'm going to probably skip an entire pipeline of events which is leading up to the search engine. One of them is a classifier, which is part machine learned, part rules-based. And that essentially tries to influence the tags associated with the story and gives them sort of confidence intervals. And then we have queries. Sometimes they can be very simple queries. Sometimes it could be a simple query which is put in the user, which is interpreted as a more structured, complex expression. But equally, and this tends to be not a very common use case, but it's very important for the financial industry. is we give them full flexibility over the search query language. We expose the search query language to them, which admittedly not a lot of people use. It's still a minority power user base which uses it, but it's equally important. So in this example, for example, you have multiple fields. You have keywords, topics, regions, sources. You have Boolean queries, proximity, zoning operators. Especially tends to be important sometimes in news because news tends to follow that pattern. The most important thing gets mentioned up front. So, and often people sometimes look for references in that. Phrase searches, wildcard searches, range queries, you want time-based ranges. Search filters, we have multiple languages. You sometimes want to filter on the relevance of the tag associated with the story. That's actually the default, by the way. Some of the interesting aspects of this is that, as I mentioned, it's an arbitrarily complex Boolean expression, and this applies to both search and alerting. I have seen users actually sort of like create 2,000 character search expressions. Don't ask me why they do it. They do it. Sometimes they almost consider it their intellectual property. They built it over years and years of experience. Sometimes it could be a list of metadata which is just specified in shorthand. Let's say I'm a portfolio manager. I'm interested in a security portfolio, which is thousands of securities. I just say, show me news on my portfolio, and that will translate effectively to an odd expression of company A or company B or company C 1,000 times. As you can see, that becomes complex from a search engine point of view, but it's quite easy for the user to enter. We have stories from over 125,000 sources. Bloomberg itself is a media company, and that's probably one of our biggest sources. But equally, we have lots of news coming in from major newspapers across the world. We have tie-ups with various research providers who provide us news. We have social media, like from Twitter. And the interesting aspect of this is that all of these sources can be turned on or off per user, and either as a matter of choice, like I'm an old school guy, I don't want tweets, for example, or just because they may not be permission for it. Some of this research content, especially sort of like people put in a fair amount of effort to produce the research content, and they obviously don't want to share it with everyone without them paying for it. So we have ACLs, which can have few, many, or all uses for each of these sources. We have searches and stories in 40 languages. One great thing about Solr Lucene is that it often comes up with very good analysis chains or ways to sort of like tokenize these languages. But especially in the sort of like, as we went through to productionization, every use case is different, and that's what you typically realize in a search engine. The way we interpret Chinese is not exactly the way Solr interprets Chinese, and so on. And that happens for every one of these languages. And any user can have a subset of these selected at any point of time, so you need to be able to accommodate for multiple languages. How we do this? We have a new search cloud which has lots of Linux machines, hosting hundreds of shards, thousands of Solr cores. There are multiple tiers. This especially helps in case of news because news tends to focus a lot on the recent stories. So you have a recent collection which we try to use first. If that doesn't work out, then we use a fuller collection, which is slightly slower. Cross data center redundancy, obviously for stability reasons, which is quite interesting from a Solr point of view because it doesn't as yet natively support cross data center. And also, at any given point of time, you could have multiple generations of collections. As I said, one of the important aspects of this redesign is to allow for easy addition of metadata. And sometimes, let's say you make a major analysis change, you have to reindex all the data. So you often end up with multiple generations of the same data coexisting and trying to sort of phase one out of the other. As I mentioned previously, stories are available for search in 125 milliseconds. So caching almost doesn't make sense in the way sort of you typically expect it from a Solr or Lucene level. There is obviously lots of caching that happens at the OS level, and we depend a lot on it. But there is almost very little caching on top of it because kind of pointless. By the time you start using the cache, it's gone anyway. We have custom components for almost everything. And I think this is what you would expect from a major installation in any case. For parsing, for indexing, for searching, for privileging, we use post-filtering. Some of this I'll go a bit more in depth, but almost everything is customized to some extent. Here's the story. So in the order in which I described, first making it work, a couple of interesting examples over there. And the way I'm going to structure this presentation is I'm just going to give lots and lots of examples. So feel free to come back to me towards the end of this talk or when we have time for questions more on what exactly are sort of the more interesting details in this. I'm just going to go through sort of one after the other kind of challenges in the almost like a war storytelling in some sort. So the first thing is to make it work, right? And a big aspect of that is to parse search queries. In particular, we have an in-house search syntax. If you recall, I mentioned that people have the ability to provide search queries in a full-fledged Boolean expressive syntax. We need to validate and privilege tags based on databases we have outside Solr. We need to present part of the search query in the UI. Even if the person specifies the UI in that native format or the expressive format, you need to break it down and present the search query in a more sort of like UI-friendly fashion, if you will. And sometimes we need to understand the query to do other things on top of the search itself. A very interesting example is that we often modify the base set of sources you're getting news from, or the set of sources we consider the most important, depending on the query. Because obviously, some sources have better information about some topics than others. So you need to often customize how you do it. So one thing we did in order to accommodate all of this is that we decided quite early on that it's not going to help us if we try to push all this complexity to Solr. So we went for there was this very old ticket which was trying to represent a Solr query in an XML format. When I say XML, it can be semi-structured. Not a big fan of XML myself. Many in this room would agree, perhaps. But the key part is that it's semi-structured, and almost very little happens on the Solr side before it actually goes to the Lucene land. So we construct the query well in advance, and Solr just reinterprets that pretty much and constructs a query object in Lucene terms. So you get through from outside Solr to a query object, which is getting searched on with minimal translation. Some translation still needs to be done. A very good example is when you specify a keyword that needs to be tokenized and broken down. And that's important, and that only Solr can do because it understands the schema. But the idea is that you allow as much flexibility as possible so that you can control the query in a tighter fashion. And it has served as well. In many cases, as I shall describe in the next few slides, sometimes we have had to do a lot of optimizations, which often means that we create new query types at Lucene level. And it was going to be a pain if we start exposing all of that in a query parser. What this allows us to do is that I can just get a builder for the class and then specify it with the arguments for the query straight away. Sometimes we needed to originally at least use a forked version of Solr. This is a fork called Flag Search. Alan Woodward, he's around if you can find him. Used to have a fork of Solr called Solr intervals, which actually helped us with some of the functionality which was not present in the Solr when we originally started it. We actually worked with him later on to get that upstream. With 5.3, that's no longer the case. But in some cases, we used a forked version of Lucene to get additional query capabilities, like kind of something like this, right? I mean, you have a phrase expression with a near query, nested near queries. Some of these sort of earlier versions of Lucene were not able to work with. The next challenge was obviously, I mentioned that we have a classification system which tries to find our tags. A very interesting idea with this tag classification system is that it has a built-in relevance score associated with it. It gives you a confidence of, if I say this story is about oil, it's 70%, I'm 70% confident it's about oil, or 95% confident about it's oil. Each story has topics, companies, regions, people tagged with it. It has each one of them has a relevance. There are multiple tags that are present per story, millions overall. And the tag relevance needed to be considered for both scoring and filtering. If you're scoring search results, if you ask for oil, you obviously want something you have more confidence it's about oil to float up to the top. You sometimes use it for filtering when you try to display results in chronological order as well. I want results in chronological order, but I want to restrict my results to only those which have oil at a very high relevance. I'm pretty sure it's oil. I don't want my feed cluttered with stories which may be or may not be about oil. So one very interesting challenge was how do we build this infrastructure in a scalable way as well as allow for normalizing relevance. Like, for example, if I have keywords Obamacare or topic health, right? One is a topic, other is a keyword. How do you normalize the scores? One thing we did was to repurpose keyword ranking for these tags. Pretty much use sort of TF-IDF, or in the future, if you come up with a different ranking, use that instead for tags as much as keywords. And that allows us to normalize. And we can also modify searches to be filtered based on ranges of these TF-IDF scores. So as far as the system sees it, it sees 70 occurrences of the topic oil, and there's a 70% confidence, or somewhat like that, at a logical scale. So that's as far as the getting stuff to work comes along. As I mentioned earlier, much of the job here is to optimize it. When we initially started off and we had the initial prototype, when we tried to push the full load through it, it blew up. Nothing came up. We did a few optimizations to the point where it at least wouldn't blow up, and we started seeing mean times of around 30 plus seconds, which is nowhere near 180 milliseconds on mean. So some of the very interesting examples here is to do with ticker list searching. As I described, you have like a huge list of companies you're trying to search on. In the naive fashion, you can do pretty much something like a Boolean of 1,000 ORs. And the challenge here was that the default setting was such that the company tag had a relevance filter set. So it was not just a term query on a company. It was actually a term query wrapped around a check of what the term frequency range was, and that with thousands of them. So we went through a series of steps to essentially condense this more and more and finally get it to a place where this entire thing can be represented by one query. And we push as much of the complexity down to the lowest level possible. And that gives us a few orders of magnitude in terms of benefit, just in terms of, and this was a very good example in which we optimized a particular Lucene query for a use case and got a very good benefit out of it. And another example for this is essentially, we have, as I mentioned, a big user base which is also interested in searching by time. There's this feature which came on quite a while back in Lucene about sorting index segments by time so that you can optimize searches by time as well. But there was support missing on Solr side, so we went ahead and implemented it and refactored a few things to Solr to be able to use that properly. So there are some changes like this which were more at the query level, which try to optimize the performance. There are others which are at a different level in terms of what the hardware we have. Goes without saying, for the kind of scale that you want, you need lots of SSDs. You can't depend on spinny disks. But there is a fair amount of tuning you can do on top of what Lucene gives by default in terms of how aggressive your merge policy is. And this is probably one thing which is often overlooked by a lot of people. You can never sort of underestimate the value that kind of tuning gives you. You often can end up sort of, especially if you have like really good SSDs, there's a lot you can do to just tax your SSD more and more, try to aggressively merge segments together so that you can get a lot more out of your SSDs, but make your searches faster. Kind of skipping over a few details here. If you need more details on this, like, please feel free to reach out to me later. So we went past that phase, and we got to a point where we optimized as much as we could, to the extent we could, and realized that a lot of the bottlenecks were going down to the Java level. Right? Searches would work out fast till you reach a point where it had to garbage collect. And for the kind of real-time latency requirements we had, there was a lot of stuff happening in the indexing side as well. And you will end up with garbage collection process for 8 seconds. Kind of pointless having your search come down to less than 100 milliseconds if you have to sometimes stall for 8 seconds. So a lot you can do to essentially sort of optimize it. Small inefficiencies multiply at scale. I think it's pretty underappreciated. You often sometimes need to know what the kernel is doing as well. Watch where the time is spent. Sometimes you can end up with a place where you think you keep trying to optimize your query, then you realize that the query is actually fast, that you're not funneling enough through it. You might realize that there might be some hard-coded number right in the code, which is actually limiting. It's like some person at some point are like, who would need more than 20 of these? Guess what? We need it. So you have to often go through that analysis to find out where that hard-coded number is or where that bottleneck is before you come up. And goes without saying, and this is more towards the operational side, you also need to do a fair amount of instrumenting along the way so that you can find that number, right? we were in a very interesting place where, how many of you guys have used YARKit? It's a profiler, which is pretty common. So the first challenge we had with YARKit was that you try to run at 2 seconds, Solr would die just like that, because there are challenges to using something as intrusive as that, even with the minimal options turned on. So you often have to sort of like build in real code instrumentation, not rely on a profiler to sometimes give you insights at scale. And sometimes this is no longer true, thankfully. I mean, we once found a case where Jetty had a bug which would sometimes stall and cause a timeout. Ramsey in my team is over here. He spent a few months trying to nail that down. And it turns out that Jetty had a race condition which used to trigger. Thankfully, again, it's not there with Jetty 9, which would cause requests to just wait for the entire timeout and then stall. Again, kind of pointless optimizing if you had to wait for 50 seconds on a race condition sometimes. Going beyond, so we got it to a place where it's fast enough. Now you need to scale things you need to make things more stable. One of our biggest challenges was to make this stable across maintenance, machine maintenance. We often have, during weekends, sort of like machines undergoing regular maintenance and hundreds of cores, essentially around a quarter to 1/6 of the system, going down for maintenance and coming back up. And those are places where the distributed coordination of a system as large as this starts getting tested. There's still lots of work going on. There's still a lot of work needed on scaling what is called the cluster state, which holds the entire Solr cloud together. But you often find out that these are things which you need to scale, and you find out only at a scale where you have like hundreds of shards, thousands of cores, that things start sort of developing cracks, if you will. Right? Note of advice: never sort of try to scale I mean, not never, but be very careful when trying to scale a Solr cloud beyond 1,000 to 2,500 nodes. That has been our breaking point. And we know what the breaking point is and what's caused by. It just needs work. In many cases, it's just an old-fashioned sort of, you shouldn't have all your leaders be present in the same place because it just tends to tax the machine out. So in some cases, you just lead algorithmic improvements to sort of help scale things better. The other more challenging thing has been that when something goes down, comes back up, it tries to recover. You shouldn't have that affect live traffic, or worse, it shouldn't affect cloud stability. We had cases where something would saturate network performance, that in turn would affect other traffic which is more critical on the machine and lead the entire cloud to disaster. In some cases, you can throttle. Not the greatest of solutions, but because your startup takes longer, but works. We actually recently moved to using a different network for this entirely. So right at the network level, we use a different network interface that needed some interesting changes on the Solr side, which we are still working on. But we at least have a solution for ourselves at this point. Using transaction log recovery, Solr uses 2 kinds of recoveries possible. You can tune this now, and this is one of the changes we had to do, so that you try to avoid copying full parts of the indexes from one machine to another, and try to do as little as possible in terms of recovering. But there will be problems. In particular, I think we started from a place where the Solr collection that we had like 8 shards, and we kept sort of doubling it up. And we figured out that each time we double the number of shards, we would find a new race condition. Right? It's almost the race condition of the iteration, or sometimes multiple of them. Good news is that you don't have to deal with this now. I think we started a place where Solr was a lot less stable with these things. So lots of work has gone from our side, from others in the Solr community as well. There's lots and lots of work which has gone into making things more stable. The nice thing here is that, well, nice depending on how you look at it. If there is a race condition, we will hit it. Right? It's just a matter of time. What happens? Is it safe to stop multiple replicas of a shard simultaneously? You would have thought so, but there is a race condition. What happens if you shut down just when the leucine index is in the middle of a merge, and the shutdown takes just a little bit longer or a little bit less, and that triggers a race condition? What if there's a delete byte query happening just around when a leadership switches, and then there's a recovery which tries to deal with the delete byte query, and that ends up stalling the recovery process by just the right amount of time to delay leadership transfer, and you start getting timeouts. All of this has like a 5-line step process, leading from one leading to the other, to leading to the other, leading to finally to a disaster. So And the funny bit is that even if you had to screw up, you had to be controlled about it. One of our changes was actually to make checks for misbehaving machines light. There was a case where there was a machine which was underperforming. All the 1,000 cores were asking, hey, are you healthy? Can I talk to you again? Yes, if you hadn't asked me, I would have been healthy. So if there's a network partition, that's the reality of life, right? I mean, like, network partitions happen. Will the cloud always heal? It should. It should. It's always it should. It doesn't sometimes. As with real life, sometimes democracy can be annoying. When you have leadership elections, which kind of say that I have to be elected democratically, I can't have a dictator, you'll end up going around in circles sometimes, one trying to elect the other. Sometimes the problem is not to do with so much with a systemic problem, but a small problem which can blow over. One of the things with infinite query flexibility is that you can have poisonous queries. I can tell you by experience that no good can come out with phrases, wildcards, and spans in excess. You'll have to trust me on this. People who try to do things, right? I mean, like, why don't I copy-paste an entire excerpt I have into the search field so that I can find the article that you have? Not a good idea, guys. The search engine is there so that you can just put a few keywords in. Or my keyboard has a key stuck. I can't figure out what to do about it. I call the IT guy up. Let me go for lunch. That thing is sending key presses all the time in the background. Solr now has better, and I haven't made this up, trust me, these happen, these cost outages. Solr now has better circuit breakers for queries. This came with around a year or so back, which is great because you should realize that a long query doesn't just have an ability to reduce your query bandwidth, like you're not just taking a thread away. You can actually take down replicas. We have taken down replicas because of one bad query, because it did so much garbage collection, it created so much garbage that garbage collection went through the roof and took the entire replica down. So it's great that we have circuit breakers, but we can do better. So often you have to account for a certain amount in terms of circuit breakers. That might be too late. So I mean, the dream would be, and we're starting to work on this now, to see whether we can have statistical query plans for searches and try to come up with models which can dictate whether a search will be slow or fast. It's a very hard problem, but we can start taking steps there. You have user replica affinity, where you often realize that people can be very persistent about their failed queries, right? I mean, like, so they've already taken down a replica because of their bad query. They try again, and you reach a point where the system tries to be nice, takes down the entire cloud for them. You need user replica affinity so that that can't happen. You need to protect the system against one user taking down the cloud. Sometimes, even if it's a systemic failure, you need to protect one system from the other. Often cases, very common cases where you have like a spike of indexing which could starve out searching, for example. Is one of the things which is ongoing in the Solr community on seeing whether we can isolate thread pools for searching and indexing. We have already worked on isolating query federation. So there's a Solr process which tries to federate out a query to multiple nodes, gets back the results. That query doesn't need to host data by its own, though it can. This again helps you to sort of isolate the federator use case from the searching use case and tune for them differently. Isolating critical roles like the overseers is something which is present in Solr. Overseer is a very critical part of the component. You can't just afford for it to go down. So you need to put it in a place where there is very little risk of it going down. The future really, and this comes back to the query plans thing, is like isolating costly queries from cheap ones. So it's not just a poisonous query. It could just be a costly query. But you don't want too many costly queries taking down the system. The other angle to this is that you often sort of like try to make things too consistent. And that's always a problem. It's all one happy cloud till garbage gets into the input. Your system just becomes as stable as what your input pipeline is. And if that input pipeline is changing, it has a bug. You don't want to end up in a system where there's bad data everywhere because you have successfully managed to replicate it in real time. So sometimes you need tightly coupled replicas, and then you need multiple copies of them which are loosely coupled, so that you can make changes to the input pipeline to one of the loosely coupled replicas, then move to the next, and move to the next, and so on. The challenge then is trying to maintain the right balance where they are loosely coupled, but you can still easily synchronize them without having to do sort of like lots of manual work. This is something which is still pretty hard, but there is work. We are working with LucidWorks and Shalin, if you're in the audience somewhere. Hey, there he is. he's working on helping us get CDCR, cross-data center replication, to get to a point where it can help the synchronization. And soon we'll be able to do this much more in an automated fashion. OK, we made it stable. Now to make it better, one of the things which we had to carry over from the old system was grouping, right? There's a different part in the pipeline which tries to collapse content which are about the same thing, but different newspapers have published it, for example. That's great as long as it's pragmatic. The problem with grouping is that, especially if you have deep pages, and again, we have seen users sometimes go to hundreds of pages, right? I mean, especially if this is their day job, they're looking through news stories, then they do tend to go pretty deep on searches. But the problem with deep paging is that, especially with grouping, there is no solution which is available to be more pragmatic about it. If the search engine starts thinking that a result in the first page could be grouped with something 150 pages later, then it has to retrieve all the 150 pages of information before it can decide on what to return. So there's a fair amount of work we need to go through to make it consider a window of end results for grouping and then deep paging. It's something we haven't contributed back, but we will eventually. One of the big cornerstones from last year for us has been to implement a learning to rank framework in Solr. This is a pretty big effort spanning multiple teams that we tried to get a standard framework within Solr where you can define features, define models, and be able to rank results, get back feature values with responses to train models offline. This is in the part of being sort of pushed upstream. There's work going on trying to commit this upstream. And if you're more interested, there's an entire talk on this from Lucene Revolution last year. Just search for learning to rank in Solr, and that will take you more. Lastly, it's not just useful to show people results. It's also very useful to show them what they should be looking for. That's the trending part of news and what I call intelligent faceting. So you don't just facet, but you be more intelligent about what you show up in those places. And this is one part where Solr can really help stream document frequencies out to a different system, which can then be used as a trend detection pipeline to consume and detect anomalies. So that's what we have done so far. There's still a lot going on in the pipeline. Relevance by itself can almost be something we can go on for endlessly, right? I mean, you can keep tuning, getting better user models. One challenge has always been sort of how you can improve what is called information arbitrage. When you have information in multiple languages, how do you get that effectively? It's better searching across news and social media. Social media, as many of you are aware, is a separate beast by itself. It speaks its own language. It has its own demographic. Trying to integrate that with news searches is a challenge. Searching and scoring effectively in bulk, we often have challenges where we need to run sort of 1,000 searches in bulk in a very short amount of time. Readership sorted views on search, self-explanatory. We have two major use cases to do with sort of chronological and relevance rank results. And often a challenge is to see whether we can combine those two workflows, get them to blend better. That's pretty much it. So that's the, I hope you can see them. That's the Bloomberg team, or part of it, which was at Lucene Solr Revolution. 20 or 30 of us working on different aspects of Solr, really. The challenges continue. Thank you.
Perfect. Yeah, just a question. How do you store your user queries, and how do you do these access control?
So can you be?
How do you store the user searches, and how do you do these access control with that? So basically, that not one user can see and destroy the searches of others.
So the user's queries are stored in sort of like, we have separate databases. This is not in Solr. We have separate databases which try to sort of partition user queries, and there's logic around trying to make them private to the user. So that's nothing to Solr. That's just a separate system which is out there, which is storing these queries. As it gets to the system, it's used in a different ways. Like not so much with search. Search is just one query getting in, getting out many results. But we often need to sort of like have in-memory representation sometimes when we do alerting. That's something I haven't touched on a lot in detail, where you try to sort of like look at all the queries and then try to find out which is there. And for a lot of this, to answer your question, privileging is embedded at the lowest level, so that there is no risk of essentially queries getting out of the system and other users seeing other people's results. So that's a big requirement in many of these, both in search as well as alerting, is you have the lowest layer, in this case, Lucene pretty much handling the privileging logic using filtering.
We've got to prepare the next talk, but please be short.
Thank you for your talk. Do metadata tags have a relation such as same as, broader, and if so, how do you query against these relations?
So the question is, do metadata tags have relationships, and how can we query these relationships? Currently, it's not part of the metadata, so we have a separate system which tries to understand user intent and converts it to query. That sometimes understands the relationship between queries, but there is a longer-term plan to actually get this into Solr index so that you can. I still don't know what we're going to do about it. It's a pretty interesting challenge. Yeah, so currently you can search for those relationships, and the index provides mechanism, but the connections are outside, and we tend to utilize them that way.
So, thank you very much.
Thank you.
Nice talk.